What is an electric field? An electric field is said to exist in the vicinity of a charged object. Let us call this the source charge. This charge generates the electric field basically. So when you bring another charge, let us call that a test charge, in this field, then it experiences an electric force. So if you have a positive charge, it generates an electric field around it. And then if you bring another positive test charge close to it, then there is a repulsive force between the two. That happens because you have brought the test charge in the electric field of the source charge. Electric force is a field force. That means it can act through space, much like the gravitational force. Two objects do not need to be in physical contact for this force to act on each other. So how do we define the strength of this electric field? So it is defined as force experienced by a test charge divided by its charge. So it's force per unit charge. It has the units of Newton per coulomb. If I have a source charge that generates an electric field and I bring a test charge of magnitude q naught close to it, then suppose this test charge experiences a force F on it, then the electric field will be given by this force divided by q naught. And you can find an analogy with the gravitational field. So the electrostatic force is given by q naught times the electric field, and the electric field is the force divided by q naught. Similarly, for the gravitational force, we know that the gravitational force is equal to m times g, the acceleration of gravity, and m is the mass. So we can write g equals the force divided by mass. So we can see the mass is acting in an analogous way as the charge in the context of electricity. And the force is the same. One is the electrostatic, one has an electrostatic origin and the other has a gravitational origin. And g kind of is analogous to the electric field basically, but for the gravitational force. Electric field lines. So we use electric field lines to represent the electric field pictorially. Field lines show the direction of the electric field. The electric field vector is tangent to the electric field lines at each point. So the density of the field lines, that is the number of lines per unit area, determines the strength of the electric field. So if the density is large, then the electric field is stronger in that region. So electric field lines actually start on positive charges and end on negative charges. They are indicated by an arrow. The tail of the arrow starts on the positive charge and the arrow points towards the negative charges. So this is basically, this direction indicates that if you bring another positive test charge, then this arrow indicates the direction in which that charge will be pushed. The bottom line is to remember the direction of the electric field lines from positive charge to negative. So this picture shows you the electric field for a positive charge. In this case, the field lines, this is an isolated positive charge. The field lines originate from this charge and go radially outward as seen. So if there is some negative charge somewhere else, these field lines will terminate on those negative charges. Now if there is an isolated negative charge minus q as shown in this picture, then the field lines actually converge inward, radially inward towards this charge. What do the field lines look like for two unlike charges? This is shown in this picture. The electric field lines originate from the plus charges and terminate on the negative charges. And you can see the density of these lines is becoming larger between the two charges. That means these charges are attracting, the force is stronger, that electric force is stronger in between the two charges. Now if you have like charges, then you look at the field lines, you see the density is very small in between the charges. The field lines are kind of repelling each other. Field lines are moving away from each other. Field plates. So you can think of two parallel plates, one positively charged and the other negatively charged. And if we draw the field lines go from the positively charged plate to the negatively charged plate, and the field lines are almost straight and parallel in between these plates. Although in reality, at the edges of these plates, the fields bend away. Those are called fringing fields. Now if we have this electric field, this is actually, if two plates have large area, then the electric field in between is almost constant, as shown by these arrows. And now if we put a test charge at point A, and this test charge has a positively charged object, then there will be electric forces exerted by the positively charged place on this object. This brings us to electrical potential energy. Because this positive charge is close to the positively charged plate, there will be a repulsive force propelling this charge, test charge, towards the right, towards the negatively charged plate. So that means there is some stored potential energy in this charge. By placing this charge close to this positively charged plate, we have given it some energy that is stored in the potential energy of this electric field. And if you were to bring this charge closer to this positively charged plate, you have to do work on this charge, and that work is energy transfer basically. So you have transferred the energy to this positively charged, and now that energy is stored. Now if you release the charge can move towards the negative plate, because the negative plate attracts it and also the positive plate repels it. So the charge is moving from higher potential to a lower potential. The potential energy is defined as UA.